Yeah, hello everyone. I'm Hao Han Yuan. Uh, I'm the second year PhD student in the Department of Information and Computer Science. My supervisor is Prof. Hao Pengzang. My research interest is mainly about the natural language processing, including large language models, especially on some large language model reasoning, some agentic workflows, and especially on the task of text summarization or information extraction. Today, our workshop's topic is reasoning for summarization in the era of LLMs. And I will, okay, so this is a roadmap for today's workshop. First, we will give some theoretical foundations for the LLM and summarization. And secondly, I will lead everyone to do the simple implementation for the LLM API and how you can use the API to do the summarization. Third, I will introduce the LLM reasoning and the adapted reasoning method for the text summarization, which include 8 reasoning strategies. And after that, I will uh, give an introduction to the evaluation and the findings behind our research. And finally, I will give some final takeaways and give some overview of the future research directions. Okay, I believe some of you have already known the concept of LLMs and abstract simulation. For the LLMs, I think most of people now are using those super powerful AI to help with their daily work, like give a drift or help them reading the paper or help them to solving some task or even uh, have some writing some plan for a travel or some just for the workshop or the presentation. So I think nowadays people are more and more depend on those super AI. And for the abstractive summarization, it's a very useful. I think most of people they are using it in their tasks. Like if you're sending a paper to the GPT and you ask it to give you some uh, key points and give you some takeaways. So that way, actually, you are doing the summarization there. And for the the definition in abstractive summation, I will give later. I will show you the some example for how it looks like. Okay. Mm, Now I will take you to say the code and how to implement it. I think nowadays you can find some free API to use in your like use Gemini API. I think most of API now are not free. They like GPT, like Cloud, like Grook. They don't have free API for the users. But I've just found that Gemini have a free API case, and you may follow my instruction, and you can apply it. For example, if you into the Gemini API page, you can uh, click API get API case, and you can click create API key. So you just name your API key. Okay, you can see here. I just create my new API case, and it have here the API key, and later we will use it. So it's free tiers. It's I think every day it have for my test it may have 100 and about 100 quota for free use, 100 calls. Okay, so at the beginning you may install some package for calling the Google API. And you can paste your API to initialize API key, and you may choose a model from the Gemini API. For example, you can see the model information here. It have different model, and once you click it, you can see the name here and the function here. And for our test use, we will use Gemini 2.5 Flash. So once you have put it in, yeah, you can see, and I will give instruction that tell the Gemini to explain what is abstractive summarization into sentences. So now it's calling. So it replies that abstractive summarization generates new sentences that capture the core meaning of the original text rather than just selecting and rearranging existing ones. This allows for more concise and fluid summaries that can rephrase complex idea into simpler terms. So that is exactly how abstractive summarization works. So I think most of you now are using the browser and using the interactive user face for the large language model. For example, you are directly using that. So the reason why we are using API, I think it's mostly because if you are doing a project, like you have hundreds of thousands and or even millions of data, and it's very normal to have millions of data. If you use a user interface, it's really not convenient. I think every time you have to retrieve the reply from it. I think but with the API, you can quickly get the reply and you can store it in any data frame that you want. Okay, so now we will show an example that use it to give get a summarization. Firstly, we give a document here, and we give a prompt that summarize the following text in one sentence, and we put our doc in here. So, and every time we call the client function, it's just need to get a model name and your prompt. And it's normally for the most useful uh, configuration you need is the hyperparameter that's called temperature and max output tokens. For the temperature, it's just define the randomness of the output in its reply. And for the max output tokens, it's give a config that it cannot give too long tokens or too short reply. So for example, here we ask it to generate a summary to for this one. And now we show for the different temperature, it's normally will get you will normally get a different reply. So if you want a diversity of replies, it's normally you can change the temperature and call the function many times so you can get many diverse outputs. For example, we show here. So you can see here if the temperature is 0, you can get this is its reply, and if the temperature is 0.8, it's get this reply. Although they look a little bit similar, I think it's because uh, in just in one sentence that it cannot and it must keep compression and keep faithfulness to the source document. So I think there won't be too much differences sizes, but you can see it's actually still have some difference here in two sentences. Okay, so okay, now I will try to show you another function of calling APIs. For example, if we give a longer document here, I have printed here. It's much longer than the previous one. And now we give the prompt. We saw that we have already given a source text. We ask it to produce a faithful and concise summary, and we ask it to return only valid JSON format. So, I mean, for the function I want to introduce is that the API normally can reply some reply the generation answers with a structural frame. For example, the JSON formats. And for the requirements, I keep asking the keep concise and make sure that what we want to include in our answers. And I asked that written JSON with exactly this case, like summary, key points, and uncertainties. So, and once you finish that, the prompting stage, you need to call the client's function, and the response type, you need to set it to JSON, and temperature and max output token. And you can see the generation output here it includes summary and it includes the key points here and some uncertainties it's extracted. So I think for some project that really need the structural data, it's quite convenient to use the JSON function to it's much easier for you to pass the generation outputs for the LLMs. And uh, one more thing, I think that you can also find the doctor that it can produce more different structural reply after if you are reading the documentation there, it's have some interesting functions there. I think oh, you can try it. Okay, now we will introduce the key concept that LLM reasoning in the now. And actually, it can generally speaking, it's a thinking mode in generative large language model. And you can see uh, it's once you give input and the reasoning means it have some intermediate steps and tokens between before gets the output. And using my own word, I think reasoning is a kind of strategies that you ask a LLM to uh, mimic the appearance like how humans think about a thing, how humans solve a task, then ask it to solve the problem. I will give an example. Yeah, this is quite a frequently used example in before paper in private papers that they at the first they are using reasoning to solve mathematical problems. Here you can see if you just ask a question to LLM and the answer normally sometimes it will give a wrong answer. But if you ask it to think like step by step, or you give some more instructions, it will produce more details and the right answers normally. So, according to many papers, that the reasoning is really help the LLMs improve its performance in many of tasks, especially in problem solving, mathematic problems, and question answering tasks. Okay, now we will give a brief demonstration of the reasoning. Okay, since later I will give more demonstration and call the API, so I use my project API that and uh, I, so I will use the GPT 4.1 model here because if I keep using Gemini, I'm afraid that maybe it will out maybe it will reach the quota of it and may it won't produce any answer here. So, but I think the function is almost the same once you have your API case, your model name, you put in the client function, and you just give your content that you want to ask, and also set the max complete tokens, and you can get a response from the for example, uh, here I'm asking a question. What's a hallucinate fact that's caused by large language models? Hallucination is also a very key concept in today's summarization task. So, as it's introduced, hallucinated facts in the context of large language model refers to information that these models generate which is false, fabricated, or not grounded in their training data or reality. In other words, the model hallucinates. Normally, we call it hallucination. And if you give, for example, if you input a paper to the LLM and you ask some question based on the paper. And sometimes it will give you some wrong answer that is not really according to or based on the paper. Sometimes it's just give you some random numbers or random answer, and may sometimes this may cause because it's the LM also have its own memories or the training data. So it's the answer may probably from its memory or the training data and not from the task and not from your instruction exactly. So here I want to show you an example that whether since I think in my slides here, the demonstration here that LM cannot really produce right answer if it doesn't think before giving the answer. The paper is published at 2022. So I think after 3 years, but for LMs, it really developed a lot of it. And whether it still needs thinking before giving an answer. So we will do I want to show you a quick example that if the problem still exists. So here I have defined a very simple mathematical problem that counts a number of non-negative integer solutions for a tuple x, y, z to the x plus 2 times y plus 3 times z equals 250 for this equation here. Yeah, and you can see I will give a very normal prompt that we use to give LM, for example, solving the following problem and tell me the answer directly. And I input the entire problem in it, and we call the LM to give an answer. So it gives us the solution to the equation. The number of solution is 451. So, and I will give a function that's do a quick check if the number is exactly what LM produce. So uh, I think a simple iteration function is enough to get exactly answer for this. You can say I use it and we count how many numbers here. So actually, if we use function to verify, the the real count is 234. So if the LM give a wrong output, sometimes it's then you cannot say it and you cannot say why it's give a wrong answer. You don't know the intermediate step why it's give a wrong answer. So that's why the thinking for the LM is very important. And now we just add one more sentence before asking to solving the problem. We Now we change the prompt to solve the problem step by step and then give the final answer. And we give the problem here and we ask it to give the final answer. So now we call the LM again. Now I will show you how it's outputs. You can see here it's outputs a lot of generation here, and it's really just like mimicking the how human to solve the problem. Uh, it's getting started to decompose the solution steps for and to the very details. For example, it has step one and has the step two here. It's really like just a counting on a paper that the students just like really solving the problem. And you can see here, step three is determining the range of Z, and step four, step five, step six, and it's began to count the solutions here. And now you can see to sum all the solution under different conditions here, and it calculates, and finally it gives the answers 234. So you can see it's actually here the same for our function to get the correct answer. Oh, I see a chat here. Okay, that that's really a good question. So normally for the tasks like question answering or no, and some problem solving or the mathematical problems, it's normally have the golden label for the middle step. And I think many researchers have developed already created some data sets that's including those golden labels for the medium steps. So you can use it to do the training for the LM. And now I think for the latest LM, like GPT-5, like Gemini 3, they all use the reinforce, reinforcement learning to um, get the thinking performance for the LM. But for the summarization task, now actually we don't have really a gold standard for the those so-called middle steps because Summarization is an open generation task. So normally, even though we have checked the middle output for that, we still don't know if it's really right or if it's really what we want. Because I think even from different aspects, from different people, uh, they may want different answer, different summaries from the generation. So they may look up to different aspects for a document. So I think normally there is no golden standard for the reasoning steps here. So, and also that's why now we are studying the reasoning for the summarization. We just want to say how the reasoning will influence the summarization and how the importance and if it really equals to the task like the mathematical problems. Okay, here I will also have a demo document show you how if we employ the reasoning strategy to the summarization. Okay, documents here, and we have a vanilla prompt that we ask the LLM to summarize the following documents into sentences. We put the document in it and we ask it. So for the normally summarization strategy, we just ask it to give a short answer. We just ask it to give a overview or summary. And for the reasoning strategy like chain of thoughts, we will add a COT sum prompt that we ask it to uh, write your reasoning briefly and think step by step. And you can see the difference between those two generation results. For the vanilla summary, it just gets the final answer. And if you ask it to think step by step, it will give the reasoning step like this. And actually, I don't really know, and I'm not sure if it's really correct for those reasoning chance, if it's really faithful to, and if it's really useful for the final summarization. And it will give the final summary. So, and that's exactly what our research want to study is that is the reasoning really help summarization. And if you check the summary answer here, uh, by using some automatic metrics, if it really outperforms the vanilla summary and in what aspects, in what metrics it can outperform, and especially for using what kind of reasoning strategies it really helps the summarization. So actually, normally the generate content is more similar if the document is not long. And okay, now I will show another example that we use the reasoning strategy, which is a variant of chain of thoughts. Here we call it the cite strategy. It means we ask the summarizer to provide a citation that which fact you have extracted and the fact from which sentence in the original resource documents. So you can see here is the instruction, and we put our document here, and we ask it to give the JSON format, output the JSON format for more easily to check, and we print the answer it gave. You can see here it's give a summary, and it give us citations that the fact it has already found in the uh, source documents, and it gives evidence. Evidence is a citation that's from the original sentence in the document. And you can say here it's provided the six facts and it gives six facts. Normally for because here I think it's quite a short summary here, but I think if you like your daily use, you put reports, you put a paper, and I think there are more facts, there are more important numbers in it you want to check, and by using this kind of method, you can uh, really check whether the facts uh, can respond to the evidence, can respond to the citation in the source document. And I think normally this strategy is especially useful for those once you want to summarize a paper, financial reports, or the medical reports that you really need very uh, correct, very faithful answers. Oh, here I just give a function that check whether the output, the evidence is really from the documents. Uh, to avoid that, maybe LLM can produce some hallucinations. So we can say the evidence provided here is really from the source document, and I just cite the sentence number is in the source document. And sometimes you can say it gave evidence that use this dot dot dot, and actually it's across different spans in the source document. So actually, it's sometimes it's quite smart to do those tasks. Okay, here I will give another conception in introduction for the large reasoning models. Nowadays, I think now we are using the GPT-5 and Gemini 3, Cloud 3, all those models, they have used the reinforced learning, and they are doing the alignment to ask the model to do the thinking steps, and to exactly make sure the model have thinking and reasoning abilities in it. So even you don't give any prompt to ask it to think, it can directly give it can automatically thinking. Like there's two examples. If you ask O1, it will automatically sort, and it will give actually the step is already in its reasoning chance, and it will produce a final answer. And for many research that they already found that the reasoning models can even produce more SOTA performance than the previous model that uh, don't uh, don't cannot do the automatic reasoning. But um, but for our here, I just want to mention our research findings that even before research that normally they believe that large reasoning model can outperform the large language model. But for our findings that if you use correct prompting strategies, those reasoning prompting strategies, sometimes even though you just use the LLM like GPT-4o, you can also outperform those reasoning models. Okay, so here we give illustration figure for the reasoning strategies we have already built and we already adapted it to the summarization. So for those 8 strategies, we categorize it into 3 groups. Like first group is augmentation, and it means we will add the actual signals before summarization, like the strategies I already introduced, like chain of thought and citation. It's all that we have called the model to produce some immediate sync steps, and after that, it will give a final answer. So this is so-called augmentation frame for the reasoning strategies. Another frame is organizations. Organization means we ask the LLM to restructure the task or restructure the input document before it's generating the final answer. And finally, for the reflection workflow, normally it's needs uh, one or more than 2 LMs to help you finish the task. Those LM will serve as an agent to help do some critique or help you refine the answers it's already the original LM have already produced. Okay, so for the next parts, we will introduce the implementation details for the rest 6 reasoning strategies. And I think now the time we can take a brief break here, and 10 minutes later, we will continue our presentation. Okay, however, we will finish the break and we will back to the workshop. Uh, so I just found a blog for the introduction for the large reasoning model. So you can see here it's listed now the different large reasoning model like Cloud 3.5, OpenAI O1, O3, GPT-5, Gemini 2, DeepSeek R1, Coastal Sky T1. And you can see that they have different students here, which means normally during their reinforcement learning alignment steps, they are using those data sets they are using those data sets, and they have some uh, golden uh, golden reasoning steps that help them to correct whether it already gives the correct answer for during the thinking steps. So after training, after multi times training, it can be more accurate and for the thinking step, and it will be more aligned with the human thinking steps. But I think normally they only focus on the task like question generation, question answering, code generation, mathematical problems, and I think so for the summarization task, they don't really have some so-called um, golden label for the uh, intermediate thinking. So I think that can explain uh, our findings that sometimes the large reasoning model also cannot really produce quite good reasoning chains. And because during the training, it don't really have the training data for the thinking steps for the summarization. Okay, now we will back to the our strategies. Okay, here we use the same document we just previously we used, and we load the LM again. So here I will show you the third strategy that's called the E to A. It's a very uh, useful strategy, especially for summarization task. And even before they have begun to use large language model, they use a model like BART or T5, those smaller model. They are using the strategies like that. It's the step for it is that firstly, it asks the model to extract some salient sentences. Actually, this is a task that's called extractive summarization. That's it won't produce abstractive sentences. It will uh, output or come from the original sentences in the source documents. And after you already extracted important sentences in the documents, then you give those sentences to the abstractive summarizer, and it will finally produce the abstractive summary. Normally, by using this way, uh, it can give more details about the facts and about the important points in the source documents. Okay, here you can see for the extraction prompt, we ask it to give some salient sentence from the documents and keep using selected sentence and return only of JSON objects. It's easy for us to parse the output, and we tell it what structure we want for. It will use a case selected, and it will give the extracted sentence in a list in an array. So, and now we call the function chat, and we pass the outputs. We can see here the output is successfully extract 5 sentences. So this answer is already passed by our function. It's gave 5 sentences that from the original document. And then for the next step, we put those uh, already extracted sentences, and we give the instruction that you should look at the important sentence first before summarization, and we ask it to give the final summary. So here we uh, I just define the prompt and do the use the chat to get the answer. And here I can show you this is the normal strategy that we use to summarize. This is we use extract to abstract. We can say it can give longer output, and when look at the details, you can see for the vanilla summary, it's just a tell left a pilot congestion pricing program. Uh, but for the extract to abstract strategy, its output, it says Reverton left a 1 year pilot program implementing what blah blah blah. So now it's give more details about the program that it's a 1 year program. And So normally when you are trying to, so this is all also a common strategy that's used for summarization. Okay, so later I will show you the differences from the mathematics or from some quantitative aspects. That's how those generated summary are different. Next, we just continue to introduce our strategy. Next strategy is the QA strategy. It's also quite common that adapt QA to the summarization task. I think QA task is adapted to many tasks, not only in the summarization, like information extraction, like information retrieval, like some um, different analysis they are using QA, which means before getting the final answer, they ask some questions about the task, and they want a model to firstly generate some answer to that and use those the important information or useful information in the answer to produce the uh, final task answer. So here for our task here, because if you selfly define question sites, I think it's not easy if you don't really have some domain experts. So one simple way is ask LLM itself to generate some questions. You can ask it to be creative or just concise or just faithful questions. And firstly, you can say, and after you generate question, I use the LM and ask it to generate the question. It's generated 6 questions about the document. And now I call the API again, ask it to answer those questions. So here is our QA pairs. You can see the question answer here. It's all about the information in the source documents. And next step, we put those QA pairs together. We dump those QAG answers into the prompt, and now we ask the LM again to produce a summary. You can see here now it's uh, produced a summary here. And if we look into the summaries we already produced, we can say by using QA, it's produced more longer summary here. Okay, for there are two metrics that's just for detecting the features of the summary. For example, the compression ratio is it means the ratio of the summary length, the summary words length, and the source document length. So if you have produced a summary that's only have half length of the document, it means the compression ratio will be 50%. And for the attractiveness, it actually means the novelty of a summary. It counts the uh, new, newly newly appeared words, those those biograms in the summary that don't exist in the source documents. So you can see the by using QA method, it can produce longer summary. I think probably it's because you have already put too many questions to ask it, and it will consider more detailedly for the documents before summarization. Okay, so for the next strategy is plan. It means we ask it to give a plan before summarization. Sometimes it's a little bit like chain of thoughts, but I think the difference between this and the chain of thoughts is that you are asking it to first generate plan, and the plan will, as input again and guide the model. Yeah, it's not really just ask it to generate a plan before generating the summary. And the plan can be you can give more definition for the plan. Like you need to check the domain of the documents. You need to have a goal. You need to define the style for your language, and you need to check if there are salient information in the documents. And you can see here it's outputs a plan first. It's detects the domain for the source documents. It generates a goal. And for the language style, it's asked to be informative and neutral, depends on the domain. And for the salient info, it also gives some uh, here information here to help the final summarization. And I think for the final summarization, it's quite similar that you just provide the information you already get, the plan you already get, and ask it to generate a summary. So since I have already generated the final summary, now in our leaderboard, we can say that compression ratio is a medium compression ratio, but the attractive is quite high. But for those two metrics, actually, it's not try to evaluate whether the summary is good enough. It's just from the aspects of the features of how it organized those sentences and the summaries. Okay, so for the next strategy, I want to introduce it called the decomposition. The decomposition asks normally it's used to those very long documents. Here, for example, I have already put a document that's taken from the archive, which is a paper. You can say I already put it in, and the total count words are 2,265. It's much more longer than the normal text. So firstly, we ask the LM to we try to split the documents into different chunks. Here, for example, we ask it to split into chunks, and for each for each chunk, you should write a one sentence abstractive summary. The reason we are doing that is if you are directly giving a very long input, normally the LLM uh, can lose focus. It don't really know which should be focused on, and it don't really know what is salient information if you input too much thing. So I think even for daily use, people are trying to split into some short steps and so that LLM can produce more accurate answer. So this is quite similar that you ask you ask the LLM to split the whole document into some short chunks. You can see here the chunks covers the sentences from uh, span 1 to 26, and it gave a summary for the chunk here. And so it's finally it gave different summary for different chunks that's only focus on the information in that chunk. And next step, we put the chunk and we put the summary for each chunk together, and we ask Elm to summarize those to give a final summary for the entire documents. You can see here is the final summary. It's still quite long because the original document is really long. And here I have one use a normal vanilla prompt, ask it just to give the final summarization. And here we can see a compression here. You can see this is if we just ask it to give a summarization. So if you want to be more concise, maybe uh, the decomposition strategy is not what you want to use. You can see here the compression ratio for the deco is much more higher than the vanilla. So because we have already gave it more trunks and the details of the summaries of each trunk. So I think intuitively it will give more long summaries. And you can see here it says certain solutions. It's say in this paper, it's say for the analysis, it's more structural for the uh, vanilla output. Okay, so for the next strategy I want to introduce it's called iterative refine. It means we ask the LM to review its summary first, and it give us the suggestion how we can improve the summary. And after we getting the suggestion, we input the suggestion together with the document, and we generate summary again. By doing those iterative loop until that LM won't give any suggestion, and it say it's already very good. So we will end the loop, and we will get the final summary that has have already been refined by the LM itself. Okay, so here is some prompt. For example, I will ask you are a summary evaluator. You will give a point 1 to 5 based on the summary's conciseness and faithfulness. And I ask the structure it will produce. So here I will directly show the iteration loop, and I will show you the output so you can know how the loop do. Firstly, uh, the LM just give a summarization, and we use evaluator. It's gave a score that's only achieved 4, and it gives some comments that like this summary is already faithful enough, but it can be more concise. So it gives the suggestions, and for the next iteration, this will together with document as input, and you can say if we output summary again, it gives a revised summary. And for the iteration 2, it already gave a point 5 that summary summary is already concise and faithful enough. So we will stop the loop and choose this summary as our final summary. And you can see the compression ratio and attractiveness here. Actually, it's also produced quite long summaries here. But I think for using, I think maybe people will ask about whether LM can really, are they qualified for an evaluator that uh, evaluates their own output? And I think the answer is yes, because from many papers and including our research that the method like those iterative refine, it's produced quite high score. Can say actually refine it produce quite high score here. Can say the uh, here it's produce very good performance than others. So it means you don't need really give special strategy or think about the intermediate steps. You just ask the LM to refine its outputs again and again. Probably you will get a much better answer after doing the loop. Okay, so for the next strategy, our final strategy is self-consistency. Okay, self-consistency means we ask different LM to output different summaries. Or you don't really need to use different LM. You can just change the hyperparameters in LLM, like the like I have already introduced the temperature or the top P, top K parameters. So it can already generate different summary and it's have different it have the diversity there and you can put input all those summary to another judge LM, ask it to judge itself which summary is better and you should choose the better summary from those candidate summaries. So you can see here, I just switch the temperature hyperparameter and I will iteratively call the chat function and it already generates three different summaries here. And because we have changed the temperature here, so every time the answer will be different. I think it's also, I think one, not most of the time, if you use browser interface uh, for those like GPT, Gemini, you can get a different answer with the same question. That's because they already set the temperature to a quite high value to keep the answer more innovative. So if you want the settled answer, a fixed answer, you can use API and you can set the temperature to 0. And for the most of times, it will produce the same output. But sometimes the outputs also will be a little bit different. That's also because the decoder strategy for the different LLM. So it really depends on LLM. Okay, so after we get three different summaries, we give it to a judge LM. We ask it to give a score to metric each summary from different aspects like faithfulness, coverage, coherence, and concision, and also can give a total score. So we ask it to give. So it's give the score for each summary, and you can see here for the total score, it's there the candidate B gets the highest summary. So after that, we will choose candidate B as our final summary. So for using this strategy, I think from our experiments, this is also a very useful strategy that's normally this can produce some summaries that are more similar to the golden label that's written by human. As you can see, if we use the rogue matrix, it's just the rogue matrix. Normally, it's just find how many n-grams are same in the golden labels and the generated summaries. You can say the self-consistent here is also gets very good scores. Okay, so uh, that's all 8 strategies. And now I will give you some findings uh, that's by we implement those different strategies and find how they affect with the summarization. For the similarity metrics like ROG and the birth score, if so, if we use zero shots, means just like our demonstration, uh, means we just give the documents and we ask it to output the final answer. And you can say the self-consistency and the iterative refine normally can get the highest score. And so that's which means actually sometimes you don't really need uh, uh, for the summarization, you don't really need uh, design strategy by yourself. You just need to ask LLM to refine by itself, or you ask LLM to generate more answer and choose the best answer from it. Then you can already get the better summary. Okay, this from the similarity matrix. And but if we use the two-shot learning, it's called few-shot learning, which means uh, firstly we give it a document, and we will give the LM two examples. For example, we give two already generate two golden summaries for two example documents, and we ask it to generate summary. We can say for the rock score, the vanilla means a very normal prompt can get the highest score. I think that's because I said the few-shot learning also can be considered as a reasoning strategy. Like you can say people you will also learn from how to solve some uh, homework, how to solve some problem before the teacher will give you some examples, some teaching examples, and show you how to solve the question, and you learn from it, and you okay, yeah, okay. So I will try to make it faster. Because since we have already introduced all strategies, and we have different findings in our papers, maybe you can check our papers to give more how our findings there. We have different aspects of findings there, and we have some uh, qualitative exemption, qualitative study for the differences. That's how the different strategies may produce some inaccurate answers there. So for our final takeaway for this workshop is that we are not real, even for the workshop, we only focus on summarization today. But I think LM reasoning is really a frontier way that's uh, diverse exploring, and I think it can be explored across many scientific domains. So I think by mimicking human experts' workflow, and you design structural prompting, or you design some strategies, some workflow for the LLM, you can really use its reasoning abilities, and you can really push the state of the art performance in your own tasks. So I think for the some method strategies we have adapted, it's not really designed for summarization at the beginning, and we adapted it to the summarization. And I think there are more reasoning methods that you can explore and you can try to adapt it to your own domain or your own task. So maybe by using this way, you can find your own SOTA. Okay, thank you for your listening. And I think now we will move to the survey.